This video is a video that helps you to explain polymers. Polymers are very rich molecules, and there are actually lots of different types of polymers that you can form. In this video, we're going to talk about radical polymerization, so using radicals to create polymers. A polymer is made of many parts. The prefix poly means many, and the suffix mers comes from the Greek word for part. So polymers have many parts. And really what they are repeating units. Now we're going to have three different examples here. One where the repeating unit is ethylene, one where the repeating unit is styrene, and one where the repeating unit is trifluoromethylene. We'll deal with these one at a time. So the general idea is we're going to take this one molecule and we're going to connect it to itself many, many times. And we're going to do it through a radical mechanism. If you read the question, it says, draw the mechanism for the radical polymerization of ethylene in the presence of peroxides. And there is the crucial thing. The peroxides are the radical initiators. The polymers that we're going to make in this exercise are things like the plastic, the common plastic in the clear plastic in water bottles, or styrofoam, or Teflon. All of those are carbon compounds, long chains of carbon compounds, polymers, made from radical reactions. And every radical reaction has three parts: a beginning, a middle, and an end. And those are called the initiation step. That's the beginning. A propagation step. That's the middle. And a termination step. A termination step, that is the end. Okay, well, we were using peroxides. Remember that peroxides are ROORs. Let me actually put that in the color that we saw it in the last video, orange. We've used these peroxides before to get anti-Markovnikov addition of hydrohalogens, like HBr. So those ROORs, those are peroxides. And what ends up happening with those is the bonds between the two oxygens, is very unstable. It breaks very easily. All you have to do is heat it up a little bit, and this bond between the two oxygens will crack open. One of the electrons will go on one oxygen, the other electron will go on the other oxygen, so you have that homolytic cleavage that creates two radicals. So this bond here breaks, and the two electrons in it become two radicals, one on each of the oxygens. Now, so far, we haven't used our building block yet. So we've just created the radicals. Now, we can start the propagation steps. And for this reaction, you want to draw four different steps, four parts, but really three of them are almost exactly the same thing. So it's really two different things. But the second thing you're going to repeat multiple times. In the first case, you're going to take your radical, and that's going to react with whatever molecule they give us. In this case, they're reacting it with a molecule called ethylene. Ethylene is an interesting molecule. This is the common name. The IUPAC name is ethene. Eth because two carbons, En because it has a double bond, and E because it's a hydrocarbon. Ethene is a hormone. It's a gas. It's a hormone for plants, not for people. And in almost all plants, it acts to ripen fruit. It's actually the reason why people in Antarctica can eat bananas. They pick the bananas when they're really, really unripe, and then once they arrive, they just spray them with this ethene gas, and suddenly the fruit ripens. That's also the reason why you can take a ripe fruit, like a ripe apple, and you can put it in a bag with an unripe fruit, say an avocado, and the ripe fruit is constantly releasing this ethene gas. That's why it's ripe. It's releasing that gas. The gas is ripening it. And so if you put it in a bag, that gas will then sink into the avocado and it will ripen the avocado. What's crazy is that we can take that plant hormone, that simple molecule, that gas, and we can make the clear plastic of plastic bottles from it. As carbon chains get longer, they stick together more. When carbon chains are this short, they're gases. As they get longer, maybe 6 carbons long, they turn into liquids. As they get even longer, say 25 carbons long, they turn into waxy solids that you can make an impression on if you press hard enough. And as they get even longer, say 150 carbons long, they turn into more rigid solids. So you can make these longer and longer carbon chains. You can turn gases at first into liquids and then into solids by putting many pieces of them together, by putting polymers of those pieces together. So everything starts with your radical. The oxygen radical is going to form a bond to one of the carbons in the alkene. So the oxygen contributes 1 carbon, the oxygen contributes 1 electron, the carbon contributes 1 electron. It's coming from the pi bond. The other electron in the pi bond forms a new radical on the carbon there. So we end up with this pi bond breaking. One of the electrons becomes a radical on this carbon. The other electron pairs up with a radical on the oxygen, and you create a bond between the oxygen and the carbon. Now let me actually do this. There we go. Okay, so now we have that new radical. So you can see that that's a propagation step. Now we're really just going to do that, but we're going to do it 3 more times. That's the whole. That may seem repetitive, but remember that that's the whole point here in these polymerization reactions. You create a long chain from simple units by repeating the same reaction over and over and over again. So in the second step, we're going to do really the same thing. We're going to treat our radical with an ethene or ethylene molecule. So notice this is going to be the same thing, but instead of the oxygen radical, we have a carbon radical. That will form a new bond to one of the carbons in this ethylene. So the radical contributes 1 electron, the pi bond contributes a 2nd electron, the other electron in the pi bond goes on the carbon, and the product here this pi bond breaks, you get 1 unpaired electron on this carbon. The other electron pairs up with the radical, and you get a new bond between those 2 carbons. So notice what we're doing. We started out with no carbon chain at all. We attached the carbon chain to the radical, and now we're adding 2 more carbons to it. The chain is getting longer. Okay, we're going to repeat that process 2 more times. So, or actually, 2 more times. So, we take this radical that we just made, and that is going to react with another molecule of ethylene. So this is going to be exactly like above, the same step. We're just making the chain longer. So this radical contributes 1 electron to a new bond, the pi bond contributes another electron to the new bond, the other electron in the pi bond goes on the carbon. Notice the similarity here. What you end up getting there this bond breaks, one of the electrons in the bond goes onto this carbon, The other electron in the bond pairs up with the radical, and they end up making a new bond between those carbons. So again, compare this with the previous molecule. We're making that chain longer, and as it goes from being tiny to being larger and larger still, it goes from being a gas to a liquid to a solid. Okay, you just want to do one more addition. So 4 propagation steps here. And I know it might seem like overkill, but that's the whole point. The whole point is that this reaction happens so many times in a row. The simple mechanism repeating over and over again changes the properties of this simple molecule so much, and it makes it such a diverse, is able to make it such, open up such diverse possibilities in terms of the materials you can make from it. So compare this with what happened above. This radical contributes 1 electron to a new bond. The pi bond contributes 1 electron to a new bond. The other electron in the pi bond goes onto the carbon there. What that turns into is this bond breaks. One of the electrons goes onto the carbon. The other electron pairs up with the radical to create a new bond between those 2 carbons. Now that happens, we've drawn this 4 times. And notice what's happened to our carbon chain. It started with 2 carbons, then 4, then 6, then 8. It's gotten really long. Even in this process, it's turned from a gas to a liquid to a pretty viscous liquid. It would have to get a little higher, maybe around 17, before it starts being waxy, being a sort of impressionable solid. And then as it gets even longer, say, to be safe, into the hundreds, it would become a sort of solid plastic like you have in plastic bottles. And so that step, just that same one step, happens over and over and over again, hundreds of thousands of times, until you have a termination step. Now, we'll draw this here, and to simplify this, instead of having a whole nother chain, to simplify this, let's use the other radical from the peroxide to cap this end off. So remember, in these termination steps, 2 radicals come together to stabilize each other. So this one radical will contribute 1 electron. The oxygen in the peroxide oxygen, that'll contribute another electron. Those will pair up and end or terminate this polymerization reaction. And what you'd get from that is that new bond there. And then you have a relatively stable molecule. And you don't have any radicals anymore, so the story of this radical reaction is over at this point. So in these radical polymerization reactions, you take a tiny molecule, in this case a plant hormone, a gas. You create a radical reaction by having peroxides, heating those up just a little bit. You get homolytic cleavage. And then those peroxide radicals initiate a polymerization reaction. They add onto one molecule to create a new radical, which adds onto a second molecule, which adds onto a third, which adds onto a fourth. Eventually you end up with long chains. The longer the chain, the more solid the plastic is. Finally, a second radical caps off the radical at the end of that chain, and that's the termination step. Now, that mechanism will be the same no matter what little piece you're adding on to it. So, if you look at this next example, draw the mechanism for the radical polymerization of styrene in the presence of peroxides. So we're still starting with that ROOR to form polystyrene. And notice that this is what styrofoam is. Before, if you just use ethylene, you get the plastic, that clear plastic in water bottles. If you use styrene, which is really similar, you end up getting styrofoam. And the styr in styrofoam is coming from this styrene compounding. This is very similar to ethylene. The one difference is you see this pH that they have there. This is a capital P, lowercase h. That's standing for a benzene ring. So let's unpack that just a little bit. Benzene is a 6-membered ring that has alternating single and double bonds. It's called benzene. When it's a branch, so it's coming off of something more important, then it is called a phenyl branch. So the molecule all by itself is benzene, but here it's not all by itself. It's branching off of this double bond, and so it's called a phenyl branch. The pH at the beginning of phenyl is what this pH is symbolizing. So when you see that capital P, lowercase h, what it really is this 6-carbon benzene ring. So we can do the same exact reaction as we did before. You would have your initiation step with the peroxides. Heat these peroxides up and they break apart into 2 separate radicals with this homolytic cleavage. Then one of those radicals will react with your molecule, but instead of it just being ethylene, this is going to be styrene. So this carbon will have a benzene ring attached to it. And so here you would have that benzene ring. But otherwise, the actual process of the reaction is the same. The radical steals 1 electron from the pi bond. The other electron in the pi bond forms a new radical. And so we would have that here. Now I'm just going to draw that in as a capital P, lowercase h, just to save space. The second one also has the capital P, lowercase h. But otherwise, the electrons move in the same way. The radical steals an electron from the pi bond to form a new bond, and the other electron in the pi bond becomes a new radical. So in our product, we will have this pH here and this phenyl ring there. But otherwise, the mechanism is the same. For the third step, same thing again. The radical steals an electron from the pi bond that forms a new bond. The other electron in the pi bond creates a new radical. The only difference is the phenyl rings that bristle off of these molecules. So notice the phenyl rings are on alternating carbons. So phenyl ring, no phenyl ring, phenyl ring, no phenyl ring, phenyl ring, no phenyl ring. So we have this phenyl ring. Over here we have the phenyl ring, and on the second carbon here we have the phenyl ring. Notice in this step it's just a repetition of the ones before. And here this radical steals 1 electron from the pi bond. The other electron in the pi bond forms a new radical. So these two create a new sigma bond. That's this bond right here. And then the other electron in the pi bond forms the radical. So you just fill in the phenyl rings, and notice they're alternating. Phenyl ring, no phenyl ring, phenyl ring, no phenyl ring, phenyl ring, no phenyl ring, phenyl ring. Okay, and the termination step is basically the same too. We just have to fill in these phenyl rings, benzene rings that are acting as branches. The radical pairs up with one of the peroxide radicals at the very end to give you your final product. And so the procedure for making this is exactly the same. So if you wanted to walk through these steps again, you can rewind the video and walk through them the first time I wrote them down. The explanation is the same. The only difference is the stuff that bristles off of the carbon chain. And what you'll notice is in this final chain, if you redraw this molecule with the benzene rings actually drawn in, so if I draw in benzene rings here, what you'll notice is that these rings take up a lot of space. And so they're going to be sort of more fluffy. They're going to repel each other more. There's going to be more empty space in between this molecule. And so it will form a sort of more foamy polymer than what we had in the last example where we just had ethylene. Because in this one, you can stack one on top of another, on top of another, on top of another. They can stack really well, and so they won't have a lot of pockets in between those chains. And so it'll be very solid. The chains will stick together a lot because they can pack so well together, they'll be more solid. But here, when we use styrene, those rings create a lot of empty space, and so this polystyrene will form a sort of airy, fluffy polymer, styrofoam. Okay, now, this next example is really, again, the exact same thing. The difference, though, is that instead of just ethylene, which is this part right here, we have tetrafluoroethylene, so the hydrogens have been replaced with fluorines. The neat thing is if we do a polymer with this, then you get Teflon. That's how people create Teflon. That's the coating in nonstick pans. So see the power here, and also notice one important principle. When you learn a reaction, when you see a reaction, don't just accept the reaction at face value. Don't just say, okay, that one thing works. Also ask yourself, what can I change and still do this? What variations can I experiment with? Would the reaction still work if I added a phenyl ring here? Would it still work if I added fluorine here? What if I added fluorine on all of them? How would it change? And then you go in a laboratory and you do that experiment, and you have a patent for a new material, or you have something new, a new piece of information that you can donate to humanity. So as you see this, the same principle, once you learn the principles, see how it can apply in different scenarios. Now we're seeing that in this example. So in this example, we can take that same mechanism that we drew for the previous two examples, and it's going to be exactly the same here. Well, actually, let me do this one. Let's start with the ethylene example, and then I'll just fill in the branches that are on these tetrafluoroethylenes. So the mechanism for this one is a radical mechanism. You know, first because it tells you here, the radical polymerization. So we're going to take this one piece, this one part, mer, and put a lot of them together, poly. And it's in the presence of peroxide, so we know that's our sign that this is a radical mechanism. Radical reactions have three parts, a beginning, a middle, and an end, and those are called the initiation, propagation, and termination steps. In the initiation step, the peroxide is heated and cracks open through homolytic cleavage to create two radicals. In the propagation step, that radical starts to add to these molecules. Now, we know all the actual reactive part of the molecule stays the same. We just have 4 fluorines on it. And so we want 2 fluorines on every carbon. But otherwise, the actual mechanism, the movement of the electrons is the same. The radical donates 1 electron and rips 1 from the pi bond. The other electron from the pi bond creates a new radical. And then we just repeat that 3 more times to emphasize this polymerization, to emphasize that you can create something new. You can create emergent properties by repeating the same process over and over again. A gas will turn into a liquid, which will turn into a solid, which will turn into an even harder solid. And so the reaction is really exactly the same. You just have these different bristles, these different hairs bristling off of these molecules. In this case, you have a lot of fluorines. But otherwise, the radical steals an electron from the pi bond. The other electron in the pi bond forms a new radical. And so you get this product. Every carbon here gets 2 fluorines. So we have these here. And it's a little crowded, but you understand the idea. The mechanism is exactly the same as before. So if you want to know the reasoning from scratch behind these, you can rewind the video and watch the process for the first one. Notice that this lone pair steals, not a lone pair, the radical steals an electron from the pi bond to create a new sigma bond. The other electron from the pi bond creates a new radical. So you create this sigma bond and this radical. And all of the fluorines are attached and bristle off the molecule. Okay, one last step for the propagation. You want to make sure that you draw these with 4 propagation steps. So in the 4th propagation step, all of these carbons have 2 fluorines on them. This tetrafluoroethylene has 4 fluorines, 2 on each carbon. The radical contributes 1 electron and steals 1 from the pi bond to create a new sigma bond. And the other electron in the pi bond creates a new radical. And so you end up with this product with 2 fluorines on every carbon. Okay, so that's the propagation steps. For the termination step, we just take that one radical at the end and we pair it up with a second radical. In this case, the second radical is going to be the second peroxide radical that we had at the very beginning. So our carbon radical donates 1 electron, the peroxide radical donates a second, and you form a bond between those two features. And so I'm just going to draw all these fluorines one last time, 2 on each carbon. And the significance of this, the reason why you get that non-stick pan, that Teflon coating, is that fluorines are very small. They're about the size of hydrogen. And so it's very hard to rip one of those off a molecule because it's not very stable. When we talk about the halogens being leaving groups, we always talk about fluorine, chlorine, or iodine, but never we always talk about chlorine, bromine, or iodine, but never fluorine, because fluorine is so small, it can't handle fitting a negative charge in that tiny space. Unlike chlorine, which is the size of a methyl group, bromine, which is even bigger, and iodine, which is even bigger than that. Iodine is ginormous. So fluorine is really small, so it's not very difficult to rip it off of a molecule. It's not a good leaving group, and so it's very difficult to rip these fluorines off of their positions and bond something else to this chain. In other words, it's very difficult to make something stick to this chain. This would be a good non-stick coating. Teflon. So the world is really your oyster with these radical reactions. The one thing I would note is they're very dangerous. Radicals are very reactive, and that's not just with other molecules outside of your body in a beaker, it's also with the molecules in your body. So if you try to do radical reactions, just be really, really careful, because if you breathe them in, they'll rip apart your tissues. If you don't breathe them in, but you come into contact with them, they'll rip apart your skin, and they can create cancers. So be careful with the radical reactions, but you can see how useful they can be in creating all these different types of plastics. From the ones that we drew here, if you use polymerized ethylene with this radical polymerization reaction, you create the clear plastic in water bottles. If you do it with styrene, you get styrofoam. If you do it with tetrafluoroethylene, and you get Teflon. If you do it with vinyl chloride, you get the PVC pipes. You can create all sorts of different types of plastics, and you can make different plastics just by adding different groups onto the ethylene backbone. So hopefully this video helped you with drawing the mechanism for the radical polymerization of ethylene and derivatives of ethylene.